Okay. Seems like we're not getting participants here, but I'm going to just start anyway. So this lecture, if you will be given here. I'll do my best to make this recording available to everyone. It would be very convenient if there were people here so I could verify as to whether my voice is getting through properly. I'm currently at my home. Hope none of you are sick. I'm not. Okay, let's get started. I have shared this the screen with the slides in it. I hope they are visible well enough for you. So today we'll start talking about covariance, correlation, and the variance of the sum. We started a little bit on the covariance already last time. So I mentioned earlier that covariance is a measure of how two random variables, how they vary together. So it means that if I take the X and I conduct a random experiment thereof, and I get some number, I do that many times over, I usually tend to get something that is very close to, well, on average, if I average them out, I tend to get values that converge towards the expected value. We call this mu of X or mu X subscript X. And then the same for Y. When we carry out random experiments, we get values on average. They tend to be, the average tends to be close to the mu of Y. These are the expected values. And if we can conduct a random experiment where we measure the random vector where X and Y occur together. This could be, for example, this could be a situation where we take a person and the random vector associated with that person is his height and weight. And let's, for argument's sake, say that the average person's height, let's call this a male person from Finland, perhaps. And let's say that their average height is 177 centimeters tall, and their average weight is about 80 kilograms. This is just for argument's sake. This may not be accurate, but it doesn't matter. When we take a person at random, many persons at random, and we look at their weight and their height, and we look at the expected value of the height above or below, negative if below, the average height of people, and the weight, how much is it above or below the average weight. And we record these and we multiply these two together and we look at that on average. Again, we are looking at expected value of this product. This is a measure of covariance. Now, what happens is that if these two variables are independent, so for instance, if the height and weight of a person have nothing whatsoever to do with one another, when you weigh a person, you know nothing about the possible distribution of the height, which obviously is not true, but if it were true, let's say we assume that, then, you know, whenever you measure a person that is very heavy, then they would be just as likely to be very tall or very short. However, this is not the case, and the magnitude with which they vary together, so high weight implies on average a higher height, and vice versa, and their covariance will be positive. And we can calculate the covariance also by looking at the expected value of the product of these and subtracting the product of the expected values. So what does this mean? What does this mean? Well, the thing is, it's not really, it's just a way of calculating it. This particular theorem hasn't got a very good intuitive explanation. I don't know that it makes sense to try and intuit this in some way. But what I do suggest is learn it because it's a handy way to calculate the covariance. Because expected value is pretty easy to compute. And if you look at this expected value here, it tends to result in complicated sums or complicated integrals if you are calculating it. If you're wondering why I'm looking at the different directions, it's because I'm looking at the windows in my screen, not looking at the camera, obviously. So this can be proven fairly easily. So we see here the covariance here of x and y is defined as the expected value of x minus mu of x times y minus mu of y. And then we do this product, we get the expected value of x times y minus x times mu of y minus mu of x times y plus mu of x times mu of y. Sorry about that should be, well, I think they all should be uppercase letters because that's the random variable is denoted by the uppercase letter. Sorry about this typographic, but you get the idea. So if we calculate the expected value, and we know that this is a sum of expected values, so it's the expected value of the sums. So this is clearly just the product of x and y here. We get it over there. Oh, sorry, this is over there. And this is the product of x and mu of y. Well, this is constant from the point of view of expected value. So this is the expected value of x times mu of y, but because the expected value of x is just mu of x, so this comes to this, and then this mu of x times y similarly becomes this mu of x times mu of y, and then this one here is just two constants multiplied together, so that's mu x times mu y. And we see here that there's a minus mu x mu y is left with these two cancel each other out, so this is the only thing that's left, and this is really the same as the expected value of x times the expected value of y. So the proof is very simple. So this is a handy way of calculating the covariance. If we have independent variables, then their covariance is 0. This is not if and only if. And I said here, consider the unit circle example. I'm not going to go through this in great detail. Let me see if I can get here a nice I think I can share the whiteboard. So if we draw the circle, and now I'm really terribly sorry about the mess here. I hope you can see this. So here's my unit circle. I'm terribly sorry about this. So let's consider the following random variable. The random variable is a random point, not inside the circle, but somewhere on the edge of the circle. I know this looks terrible, but I don't have a good tablet to draw. So that's a random point. And let's say that it's picked randomly from x and y, and then, once we know x and once we know y, or once we know y, we know both of them, right? There's only two possibilities. If we know that x is here, then we know that y is one of these. So clearly x and y are not in any way independent because one almost uniquely determines the other, right? So the probability of getting a positive or negative, that's not affected by that, but it's impossible for y to be 0, which occurs here and here, if x is here. Instead, y can only be one of these two values. However, y can be either positive or negative. And if we really intuit, I'm going to just see if I can. if we really intuit this and look at the definition, sorry, I'll reshare this. If we look at the definition here, covariance will be 0 because when x is negative, then y is equally probably positive or negative. And the same for y and x. However, they're clearly not independent. So their covariance in this situation will be 0, but they're definitely not independent. Okay. So it's really important to understand that covariance measures only linear dependence. Linear dependence meaning linear in the sense that to what extent does one grow in a straightforward manner or in some straight line linear kind of manner when the other one grows, or if it's negative, then it can go down. So if covariance is positive, then the deviations from x and y from their expected values is more often in the same direction. So bigger values of x imply bigger values of y on average. And if it's negative, then bigger values of x imply smaller values of y. The magnitude of the covariance, however, is problematic because it depends on the variances of x and y, and it's not independent of the magnitude or scaling variables. So for instance, if we have the covariance itself does not necessarily tell you how strongly they are dependent. So if we have, let me just do another share. Let's do another share here. Whiteboard, share. So let me see, clear this. And let me do another idea here. So if we have here, this is my sample space. And let's say this is my, again, I'm terribly sorry about the bad quality, but the sample space, it's supposed to be something like this. So y is between these values here, and x is between these values here. So let's say that it's uniformly distributed. So we take random samples, we get, we get points. Let me see if I can have a nicer. Oh, that's not, I wasn't supposed to do that. Sorry. No. So let's say that we just get a scattering of points in this so 1 point over there, 1 point over here, another point over here. It's uniformly distributed around this area here. And this is not up to scale, but let's assume that on average, this is the both have the expected value 0. And sorry about the bad drawing. I'm not really good at drawing by using the mouse. So if you consider this situation, then you would expect the covariance to be relatively big right here. So the covariance depends, but if you scale this, let's say that this one originally is 1, and this is -1, right? So if we multiply this in such a way that this becomes 10 and this becomes -10, so this x-axis becomes stretched like this. What happens to the covariance? Well, the expected value, whenever x is big, it tends to be bigger. Here when it was 1, then if we know that it's bigger, that it's uniformly distributed. So x is between 0 and 1, and let's for argument's sake say that on average it's somewhere over here. It used to be 0.5, but now it's 5. So the variance of x has grown, and we already saw how much it grew. The variance of x grew sorry. The variance of x grew, and we saw this from the last one, that if you increase, just there you go here, if we increase, multiply x, you can think of this b here as being 0. If you multiply x by a, then the variance becomes actually multiplied by a squared. So it has 100 times bigger variance. And I'm not going to go into detail there, but the variance, the covariance will be roughly 100 times bigger if we do that scaling. So in order to normalize this, let's take the standard deviation. Remember, standard deviation is a measure, it's a square root of variance, and it's a measure of, on average, or the expected value of well, it's the square root of the expected value of the distance of the square from the expected value of x. Meaning, that is roughly the distance, expected distance at which each sample point is from the expected value. So when you take a random sample, it's not, on average, they tend to be around the expected value, but because they don't exactly hit there, then the average one of those has a distance which is roughly the size of this standard deviation. And it turns out that if we take these normalized variables, so if you look at this, let's call this hat x here, this hat x, and it's x divided by the standard deviation of x. So if we take the variance of hat x, then it's 1 over this sigma x squared, because that's squared, times the variance of x. But the variance of x is sigma squared, so that amounts to 1. So now this has variant, when we normalize it like this, we get a variance of 1. The same we do with y, so we get a variance of 1. So these normalized variables now, whenever we take this one, it's scaled so that it has always a variance of 1. And now, if we take these normalized variables and look at their covariance, then their covariance is independent of, turns out it's independent of the variances of y and x, because we removed the effect of the variance of x and y. So we kind of compressed or stretched these distributions so that their variance is normalized. Without changing, this changes the expected value, but it doesn't matter how it changes the expected value, because we are only looking at the relative magnitude at which x and y vary together, or whether they do vary together. So let's look at this. Then we calculate the covariance of these normalized variables, and what we get, in fact, by calculation, so this is expected value of their product, and this is the product of their expected values. So from here, we get, from both, we get really the multiplier 1 over sigma x times sigma y, because both this term, if you take 1 over sigma, that has x over sigma, and that x, and this has y over sigma y. So we take the 1 over sigma x sigma y as a multiplier, and then we get that times expected value of x and y. And the same happens here. They just come here separately. We can take this as a multiplier for this, but this is just a covariance of x and y. So if we divide the covariance of x and y with both the standard deviation of x and the standard deviation of y, we get the covariance of these normalized x and y. And we call this quantity the correlation of x and y. So the correlation has this property that it's like a unbiased measure of this dependency, linear dependency. It's called also a linear correlation. We can do some functions on x and y to conjure up other kinds of correlations. So they may have correlations that are not linear, correlations that's, here we call correlation only the linear correlation, but they may have some dependencies that are non-linear. For instance, like the example that if x and y are on the edge of the circle, so they have a very tight dependency. However, their linear covariance and linear correlation as a result is 0. But there's clearly a very strong dependency on them. So now we have this, you've encountered correlation before, I'm sure of it. So here you see, this is called the correlation of x and y, and we can get it by calculating the covariance and dividing it by either the product of the standard deviations, or alternatively the square root of the products of the variances, because it's the same thing. And let's take an example here. We have the previous example where we had the density function f of x, y when 0 is, oh, why is this missing? Yes, yeah, so we had that 8 times, sorry, this should say 8 times x times y. Okay, sorry about that. So f of x here should be 8 times x times y. I'll write it here. I'm not sure if the message is so. This is f of x, y is equal to 8xy. I'm not sure if this is visible to you. This message is from the recording, but that's what it should say, 8 times x times y. We already calculated in the previous example that the expected value of x times y is 4/9. I'll just skip back to that example. I should have the where was it? Here, this is the example. So we have here f of x is x times y. We calculated the expected value of x, y. I did that in previous lectures, so we established that that's 4/9. Revisit the previous lectures recording if you want. I think I did this by hand. Now we have this 4/9 as the expected value of x times y. By similar methods, we can calculate the expected value of x. We just take 8xy, so we have here 8x squared y dx dy. I think we did this already by hand. I'm not sure if we did, but this is a good exercise to do. You can fairly easily do so. If you do this as first approximation, first integrate over x, then you get that's 8/3 times x to the 3 times y, and then you substitute in that at the lower limit 0, well that's 0, at the upper limit y, so that becomes that's y, the first integral, the inner integral becomes at 8/3 times y to the 3 times y, so that's 8/3 times y to the 4. And then if we take the integral of 8/3 times y to the 4, if we take the integral of that, then we get 8/15 times y to the 5. And then we substitute 1 at that, so it comes out at 8/15. And then the same we can do for y. I'm not going to go through the details. You can do it by hand. I have full faith in you. First x from 0 to y, and then y from 0 to 1. You get 4/5. So we can multiply these two together. That's 8 times 4, which is 32, 32 over 225. And so we have 32, we have 4 over 9 minus 32 over, no, 5 times, sorry, what am I talking? 5 times 15. Did I miscalculate this? 5 times 15 is 50 plus 25, so that's 75, right? So, well, that's what we need to calculate. Why am I having 225 there? That's about 3 times that, 3 times 75. 225. Well, I'll trust this. I'll trust that that should come out at 4 over 225. So the covariance is that. The variance, on the other hand, of x, we can calculate that by the expected value of x squared. I'm not going to do that. You can verify it minus the square of expected value of x and so forth. We get 11 over 225 and 6 over, so that should be a capital Y, 6 over 225. So we get that the correlation is a 0.4, just doing the dividing this by the square roots of the product of these. Didn't verify 66, 225, 225 is canceled, so that's 4 over the square root of 66. So we get roughly 0.4924. So that's a correlation which is positive. They vary together in the same direction. And this is like an independent measure now, the correlation. The covariance itself doesn't tell you a lot. You have to know the variances to assess that from covariance. But this correlation, you can think of it as the normalized covariance. It's always between 0 and 1. So we can prove the following theorems, and I'm not going to go into why the proofs of these. So we can prove these as theorems. I'll talk about a little bit more about this. I have some exercises put there that will help. So the correlation is a quantity that is always between -1 and 1. And if the x and y are independent, then it's 0. If x and y have some dependency, it may be 0 or not. The thing is, if it has a linear dependency, and here the second part, if the correlation has an absolute value of 1, if and only if, with probability 1, there exists some fixed A and B, such that with probability 1, y is always ax plus b. So that, and if this A is positive, then the correlation is 1. If this A is negative, then the correlation is -1. So this is why we said that it's linear correlation. It measures linear dependency. If there's a complete airtight linear dependency, then the correlation will be 1. And it will be exactly 1 if and only if that's completely airtight. So it's a 0 probability that we get anything else. Here's some scatter plots with different correlations. So if for instance, the first one with the correlation about 0.7, we see a clear dependency or clear tendency for this. If we have here, if we think of these scatter plots, and we have a tendency of x to be, let's say the horizontal axis is x and the vertical axis is y. So when x is bigger, then y is also bigger. It's not completely airtight, so I'm not sure if I don't seem to be able to select anything there. But if you look at somewhere in the middle of the picture, there are dots that are, if you go middle way of that scatter plot horizontally, then you will see that there are dots quite far to the left and quite far to the right. But then as you go higher, then the dots tend to be towards the right. And when you go down, the dots tend to be to the left. So you see that there is a dependency but it's not perfect. The second one, it's just, you can think of this as the other way around. It's negative because when X tends to be big, Y tends to be small. On the third plot, these dots fall perfectly on a line. Well, they don't actually fall. If you look at it closely, there's a slight misalignment there. It should be something like minus 0.99999 or something like this, because but it's very clear that there is a strong dependency. But to understand, I mean, it's also clear that there's a very strong dependency in the last picture with this rho equals 0, so that rho is usually used as symbol, like sigma is used to denote covariance, then rho is often used to denote the correlation. So in the fourth picture, the correlation is 0, but it's clear that they are not independent. I mean, this could be a very close fit to a quadratic model with a negative coefficient. So y is something x to the some negative value times x to the 2 plus something, or shifted a little bit, right? You can see this. It looks like there might be a quadratic, but in any case, it's non-linear dependency, and it doesn't have this tendency where it's always growing when the other one is growing. So be mindful of this. Correlations of 0 do not mean that, that there is no dependency. Correlation of 0 just means that you can't say that when one grows, the other one always grows as well, or one grows and the other one goes down. But you can say if there's a negative correlation, then they have a tendency of going so that X is going up, then Y is usually going down. More accurate analysis of these dependencies with multivariate or random vectors with many components can be done with regression analysis. We're not dealing with it in this course a lot. I'm not sure if this is a little bit towards the end of it. I think we're going to have a little bit of regression analysis if we have time. It's actually, regression analysis is a pretty good tool for eking out linear dependencies. And then there's nonlinear regression, in which you have to somehow guess the form of the dependency function or something like this, and do the analysis then. I'm not going to go there now, but you have to. I'm just saying that please be aware of it, and please also be aware that correlations per se. This is saying correlation does not imply causality, but correlations per se are not. They only imply that there is some kind of a tendency of these to work together or occur together. It doesn't imply any kind of a causal link between two variables, but you should know this already by now. If we have two random variables, X and Y, and we add them together, then if we take A times X plus B times Y, we take some linear combination of X and Y, then the variance that you get is A squared times variance of X plus B squared variance of Y plus 2 times AB times the covariance of X and Y. In particular, if they are independent and the covariance is 0, again, sorry about the mismatching typography, it should be capital or uppercase X and Y there. Here, that's lowercase, it should be uppercase, sorry about that. In particular, if they are independent, then the variance of a linear combination, you get this kind of a quadratic combination of variances. This is actually a very strong and powerful theorem that is often used in preparing for, let's say, disasters, or preparing for different kinds of risks. Let me give some example, for instance. So let's say that there are two companies out there. There is a travel agency that makes a lot of money if there are no virus infections or epidemics going on. On the other hand, there is a hand sanitizer company that makes a killing if there's a big epidemic. So you are at a situation, it's, let's say, assume that it's about roughly, you've gotten some money from your relatives, elderly relatives around Christmas time. And you have to, you've decided to invest that money. And do you invest in a travel agency or do you invest in the hand sanitizer company? Well, if this was Christmas of 2019, then knowing what you know now, you'd probably invest in the hand sanitizer company or the toilet paper company, but not in the not necessarily in the travel agency, because they're not going to make a lot of money now with all the travel bans. So what you want to do, I'm going to move this window so I can look, I'll be looking a little bit closer to the camera. So what you want there is to prepare for the contingency without knowing it. So you know that the hand sanitizer company's stock goes up when the travel agency stock goes down. In a normal summer or a normal springtime, there's going to be a little bit of infections and not by much. But you know that in the worst case, one has a really bad outcome and one has a really good outcome. In the other direction, it is a very, let's say it's very sunny and very nice weather. People travel a lot and then no viruses or anything and people don't worry about anything. The hand sanitizer company doesn't make a lot of money, but the real issue is the actual situation usually is somewhere in between. So their covariance is going to be negative. So the variance of this portfolio, you use some of your money to buy the hand sanitizer company stocks and some of your money to buy the travel agency stocks. This A and B, you know, these could be the number of stocks you buy or some amount of money you invest in them. And this is how much risk you take in. And no, this is that because the covariance is negative, then this tends to be small, tends to make this variance smaller than simply this. So if they're independent, this is the kind of risk you take on, but if they're not independent, you add this. And this, if this is negative, then you lower your risk. The expected value is simply the linear combination of these, but the variance is this. So that means that there is less variability there. And so this is, of course, a silly, childish example, but it's supposed to illustrate a situation that you can have two random variables, and if the covariance is negative, then you can combine them to come up with a random variable that has far less variance. Because, for instance, if this is if you think of these as percentages of your investments, then if this is 50-50, then this is 0.245, this is 0.25, and if this is negative, then this is far less risky, if you will, than simply putting all your money on X or putting all your money on Y. And even if they are independent, then if you think about this, then the variance will be smaller here if you put half your money on X and half your money on Y, because they are independent. One goes down, the other might still go up. Okay. To prove this theorem, this one, that this holds, we know that the expected value of this linear combination is the linear combination of, linear combination of the expected values of X and Y. I'm sorry, there's a bad subscript there. That should be a Y. Okay, I'm sorry. I was working on this last night and I made a obviously made some kind of error here. Now, okay, that should be y, the one that I highlighted. All right, we look at the variance of ax plus by. So it's the expected value of how much does ax plus by differ from this expected value, that to the power of 2, and then we look at its expected value. This is just the variance of that. And we can calculate this by taking the expected value of the square of this here. We have a times x minus mu x. We can, so this is a, look, this is missing one. Okay, just a sec. Where did I put my pen? Well, let me write it here. So the first one is this is, we are looking at a times x plus b times y, and minus, now this is in the expected value. I'm going to write just one. So this is the something that happens in between. I hope you can see that expected value of ax plus by minus a times mu x minus b times mu y. And now we can group these together, This, sorry, it's not exactly that. It's, sorry, I missed one thing. So that is inside, and that is taken to the power of 2, right? That's what the should be. This should be between here if you wanted to make it a little bit more visible. So and then we do this, we raise this to the second power, so it comes out to this horrible thing. And when the dust settles down, what we do is we get this. Not going to go through all the details, but you see here, the important part here is that the covariance is added to the variance. Let's say in particular, what in particular comes, let's say that we take x plus x, where x obviously has a covariance of x with x is the variance of x. So this comes down to a squared plus, this is the variance of ax plus bx, so that's a plus bx. So this comes down that a squared plus b squared plus, and then this is just 2 times ab times the variance of x. These would all be variances of x. So what we get is, in fact, a plus b squared. So the sum a plus b, and that sum is squared times the variance of x. So it's just as it should be. If x and y, if all these x's are independent, then the variance, the sum of the linear combination has a variance where it's a linear combination, but the independent multipliers are all squared. If we have two random variables x and y in this example, and they have variances 2 and 4, and a covariance of -2, and we calculate a new variable u, which is equal to 3 times x minus 4 times y, and we look at its variance. The 8 here has no bearing on the variance, and then there's 3 squared plus this, so that would be 9, and that would be 16 times, that would be 9 times 2, that's 18 plus 16 times 4 plus 6 times minus 4. Why is this -4? What did I do wrong? There's a little bit of a, this is wrong now, because it should be 2AB, so that's 2 times 3. Oh, yeah. That's 2 times, this is A times B times this covariance, which is -2. So it comes down at variance of 130. This is a pretty big variance with this. And notice that this takes the covariance is negative, and we are subtracting this y. So in fact, -4y will have a positive covariance with x, because with 3x, because it has we changed the sign, right? You have to understand, if x and y have a negative covariance, then x and -y have a positive covariance. Should not come as a surprise. All right, so now we have these measures. We're going to be using these measures when we analyze some statistics. I mean, we're not going to look at a huge deal of examples here. We'll look at through them towards the end of the course. So we are heading roughly towards the halfway of the course. So this is the third week of lectures, and we have 7 weeks of lectures. So we are soon approaching the halfway of the course, and the first half will contain these probability theoretical tools, and then the latter part will contain some methods for statistical analysis. Very rudimentary, but you know, to get you started and at least be literate about certain statistical analysis tools. But before we do that, I want to talk about 2 more things. Chebyshev's inequality and moment generating function. This last topic of this lecture will contain these 2 things, last 2 topics. So the thing about it is that very often we've kind of maintained here that we know the distribution of x and y, or somehow have eked out the covariance or the variances and so forth, or that we know for a particular variable, we know the density function. But that's not usually the case. What is more often the case is that we may have some idea of the expected value, and we may have some idea of the variance, but we don't know what the actual distribution looks like. We only know these 2 things. So the variance itself can tell us how far the expected value, how far from the expected value random values end on average, or the square root of that. And if we know nothing else about this, then we can come up with only rather not very good approximations of probabilities of how often some rare occurrences or rare events occur. So many of you are familiar already a little bit, at least, with the normal distribution. We will talk about it later, but the normal distribution is a very well-behaved distribution, in the sense that it has this bell curve in the density function, and then there's a standard deviation or the variation. And then as you move further and further from the middle, then or more and more in terms of how many times the standard deviation. So there's STD1, STD2, STD3, and so forth. And these become increasingly and exponentially rarer occurrences. Not sure if you remember this, but when they were looking for the Higgs boson, for instance, they were doing a ton of experiments, and there's a lot of random noise in those experiments. And what they were looking for was a confirmation that a certain thing occurs. And if it were just random noise, then they were talking about 5 sigma level. That means that that particular occurrence would be a product of noise only in cases where it's rarer than 5 times the standard deviation. If it's a normal distribution, then this is going to be an astronomically rare event. But what if you don't know the distribution of that? So the only thing we know is expected value and variance, but not the distribution itself. So what can we do? That's where the Chebyshev's inequality comes to play. We'll prove this, and it's very simple. It's not a very powerful tool because it doesn't give you very small probabilities. So let's look at this. The Chebyshev inequality says that the probability that x minus mu, that's x is how far x is from its expected value, that the probability of this is greater than or equal to the t. So this is some measure. It's always smaller than or equal to the square, so the variance divided by the square of t. Or equivalently, you can express it. The probability that x is closer to mu than t is greater than 1 minus sigma over t squared. So as you get further, as this t becomes larger and larger, here larger and larger, or smaller and smaller if it's very, 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 well, larger and larger if, yeah, sorry, not smaller. This is absolute value, so this is always a positive. As t becomes larger and larger, then it becomes rarer and rarer. And how fast it becomes rare depends on the variance. Alternatively, it becomes more and more likely to get values that are closer than t to the expected value. So this becomes smaller, so this becomes closer to 1. It doesn't matter what that t is. In particular, if we move k times the standard deviation away from that expected value, then the probability goes down in a quadratic manner, 1 over k squared. So 5 sigma event, if you will, cannot happen more often than once in every 25 samples. Well, that's not a very good result. Sorry about that, my nose is itchy. It's not a very good result if you are looking for very, very rare events. So the 5 sigma event itself is not going to be all that uncommon unless you know something more about the distribution. Well, very often the case is that we know that the distribution is some more well-behaved distribution. If you know nothing about the distribution, then 5 sigma event is, we know it's not more common than 1 in 25. I mean, you can look it up how rare they are in 5 sigma events are in normal distributions. That's like 1 in a billion, or something like this. I don't remember, it may be even less. I don't remember exactly. This is surprisingly easy to prove. We do this for continuous variable. We don't know the density function. All we know is f of x. So we calculate the probability. So we calculate the integral over all those values where x minus mu is greater than or equal to t. The absolute value of x minus mu is greater than or equal to t. So should I draw a picture? Maybe I'll draw a picture. Let me see if I can make a picture of it. This is my ugly picture. All the pictures will be uglier even. So here's my, I didn't mean to be that ugly. So here's my axis. Okay, let's say that's 0. Let's say that's the expected value roughly. And here's my density function. Maybe it looks something like this. And my, let's say my standard deviation, this is my sigma. This is my minus sigma. This is my x, right? And now, let's say here is my t. Here's my minus t, right? So I'm calculating the integral of all this stuff here. Okay, just a second. How do I get this out? I managed to somehow, I managed to somehow lock my view in such a way that, okay, I'll close that. And share. Okay, so I'm integrating over those tails. So you see here x minus mu is greater than or equal to t. So I'm integrating over those tails. And now, if you really think about it, that's f of x, and we are further away. We know that in this situation, I'm going to write this message, and I really hope that it works. So x minus, because x minus, the absolute value of x minus mu is greater than t or equal to, I'm going to write it like this, but it doesn't really matter. Then that implies, of course, that x minus mu squared is greater than t squared, right? In particular, it means that x minus mu squared divided by t squared is greater than 1, right? So that's how we get here. This is 1 times f of x, and we know that this quantity here, in the area over which we integrate, this is greater than or equal to 1. So it means that this probability here and this integral here is smaller than or equal to that. Whatever that is, we multiply it by something that is, whatever this f of x is, we multiply it by with something that is greater than or equal to 1. So it's going to be greater than or equal to whatever this is. Because this f of x is a density function. We don't know what it is, but we know it's non-negative. We multiply it with something that is greater than or equal to 1, then it can only become bigger. Here we take 1 over t squared as the coefficient, and we calculate this. Well, here we are integrating over these values. But this here that we are integrating, the integrated function, that's actually the one that appears in the integral of the variance. So if we, instead of integrating over this smaller region, we integrate over some larger region. And note that this is a positive quantity. This is f of x, it's a positive, non-negative quantity. So this is non-negative, and this is non-negative. So if we just increase our area, surface area of the integral, or increase the scope of the integral, then it can only become bigger. And this here, this integral in the last bit, this integral here, it's simply the formula for the variance. So we get variance over t squared. So that's the proof of Chebyshev's inequality. It doesn't give you very good tools here. Especially, it doesn't say anything if t is, if this t is smaller than or equal to sigma, because then this is just, this is just greater than, probability is smaller than or equal to 1. It doesn't say anything. So the thing about it is that if t is 2 times sigma, then the probability is at least 0.75. A random variable is closer to the expected value than 2 times sigma. And 3 is roughly 1 in 9. It should be 25%, the first one. That's not 75. It's, closer. 75% is the probability that is closer. So it's less than 25% of those are further away from that. So this is a bit confusing text. If t is over, then the probability of at most 1 over 9, the random variable is outside of range. So this is the first example. So here's an example of a ball bearing that has a diameter of X millimeters as a random variable. Expected value and density function are unknown, but we know that the variance is 0.09 millimeters in squared. I mean, it's the square root of this. It's actually the standard deviation is 0.3 millimeters. A randomly chosen ball will have a diameter of more than 0.7 millimeters of an expected value within the probability sigma squared over 0.7 squared. And we can calculate that. I actually didn't, for some reason I didn't calculate. You can calculate it. 0.09 squared over 0.7 squared. Let me just pop up the calculator. So I'm just going to calculate that off screen. 0.7 squared, and you divide that by sorry 0. Of course it's 0.49, so 0.09 divided by 0.49, so it's 18%, 18.37%. So that would be 81.63% of all those balls will be within tolerance if you have a 0.7 millimeter tolerance. All right, we'll be having some examples of this Chebyshev inequality. We're not going to be using it all that much during this course, but I really implore you to understand that that's it's a heavy duty tool to give a upper and lower limit for some of these quantities or these things. Some of these probabilities. Usually, if you know the distribution, it will be you will get a far better approximation of upper limits of how rare certain events are. This is absolute maximum. All right, one last thing about this this time, the lecture. Oh, sorry. I'm gonna have to share again this. All right. So the moment generating function. This is more a theoretical tool here, but I'm going to explain it because it's I'm not sure if some of you have studied physics and those kind of things where you use Laplace. I mean, in certain theories, you use Laplace transform or Z transform in the discrete case and so forth. I'm going to get there. Don't worry about that, but I'm going to put some groundwork here first. So we define the kth moments about the origin or around the origin, but I think for some reason most literature says about, but around the origin is, I think, preferred, is the expected value of the kth power of x. And kth moment about the mean or around the mean is the expected value of x minus mu to the power of k, where it means, you know, you saw already that the second moment about the mean is variance. We've seen that already. So we have the expected value. We can think of this as first moment around about the origin, corresponding to the center of mass of the probability. And the variance is the second moment about the mean, so that means it corresponds to the moment of inertia around the center of gravity. And we are dealing with one-dimensional objects, so we don't have to define the axis here at all. Usually we would have to, if we'd have a vector variable, we'd have to define the axis and so forth. We can do that with covariances, but don't worry about it. We don't have to talk about that too much. So
We already saw that sometimes the expected value of x to the k and the kth moment about mean, and I mean this expected value, meaning that the first moment around the origin doesn't even always exist. We had an example of a random distribution that has a perfectly legitimate density function, but no expected value. So when there's no expected value, then obviously there is no possible way of defining the kth moment about the mean either. So when we move on, we should always assume that these quantities actually do exist. One way to compute these momenta, well, it's really moments, is by forming the so-called moment generating function. And the moment generating function of a random variable is defined as the expected value of e to the t times x. Now, that's not meant for you to understand in a way that, okay, you're just going to calculate the expected value of some exponential function. This is a theoretical tool, very similar to the Laplace transform and the Z transform, which I hope are familiar to you, but if not, don't worry. I'm not going to use that theory here. For discrete variables, the moment generating function t, mt, is defined as you just calculate the expected value of tx, e to the tx. The same for continuous variables. Please note that in this definition, e to the m0 is always defined because the density, for density functions, both this sum, if you put t at 0, then this e to the tx becomes 1, regardless of x. If t is 0, that's e to the 0, so that's 1. So this is simply 1. M0 is always 1 for all legitimate distributions. The same here, because this integral over fx dx in the sample space is going to be 1, and for t equals 0, this is going to be, this e to the tx is going to be 1. So this is just going to be 1. So m0 is 1 for all density functions. And at m0, that always exists. If you go to values greater than 0, then it might not exist. Well, if you go to negative, on the other hand, it might exist even when things like the expected value don't exist. Doesn't matter. So here's a theorem which we will not prove. But the thing about that is it's not unlike the Laplace transform theorem, which says that if you have the Laplace transform of two functions, then if the Laplace transforms are equal in some interval that contains 0, then the functions are equal. Yeah, for analytical functions, this is true. So in two random variables, x and y, they have the same sample space and same moment generating functions in some interval that contains 0, then x and y have the same distributions. That's really important to understand. We're not proving this theorem, but it proves, if you look at Z transforms and Laplace transforms, you should, at some point, you can revisit this. If you, I'm terribly sorry about this yawning. I've sat here for too long. So this is also very interesting and useful in moment generating functions. The moment generating functions, if you take this m of t and you take its derivative, kth derivative, then what you really get is the kth moment about the origin by definition. So the kth derivative of m at 0 is the expected value of x to the k. So this kind of ties the once you know the moment generating function, you can perform this expected value operation by carrying out a differentiation of the moment generating function. we can prove this. The thing about this is that you can take the expected value of e to the tx. Remember the expected value here we use, I mentioned it. Those of you who are not familiar with operator theory, just mentioned at some point that the expected value is a linear operator. A linear operator like the differential operator. So the derivative is also a linear operator. So when you take the derivative of a times f, then it's a times the derivative of f, when a is a constant scalar value. So it's the same thing happens when you do the same with the expected value. So that the kth derivative of e to the tx is the expected value of the kth derivative of e to the tx. And because it's you're differentiating with respect to t, and you're looking at that t there. So if you do this, then you find that that should be capital K, capital X here. If you take the derivative of e to the tx, that's x times e to the t. You take it second time, it's x squared times e to the t. You do it k times, it's x to the k times e to the tx. That should be a capital X here. Sorry, I made this mistake here. And if you substitute for t equals 0, this becomes 1. So that's just expected value of x to the k. And this has the consequence that, for instance, the expected value of x is simply the derivative of x's moment generating function at 0. And that the variance is the second derivative minus the first, it's the square of the second derivative. I'm not sure if you've studied the way that Laplace transforms can be used to solve differential equations. If you haven't, then forget what I'm saying. But if you have, please check that there is this way in which we can solve linear differential equations using this. I taught this a couple of years ago. That's course. So I'm not going to go into the detail, but you can revisit that if you know the material. Or later, if you encounter this in differential equations or some other topic where this Laplace transform is used, then please refer to this. There's a very high level of similarity there. Now, if we have the moment generating function of x, it's given as mx of t, and we impose a linear transformation on x so that y becomes a times x of b, a times x plus b, then the moment generating function of y can be calculated by, it becomes e to the bt times the moment generating function of x at at. You can verify this fairly simply. I put this as an exercise for next week, so you should be able to tackle it. All right. That's the theoretical material here. And now I'm really sad that, not sad, I'm not sad, I'm not crying, but I'm a bit disappointed that I was unable to gather any audience here because I had reserved 15 minutes for questions. It seems as though that 15 minutes is not going to be used. It's too bad. Nobody came. I'm going to record this, and I'm going to hope that this recording I can share. I have no idea if it can be done. So if you are somehow hearing this and seeing this, then I have succeeded. If not, this thing will go into big heaven. Okay. We'll reconvene on Friday at noon, I think. And then we'll look at the examples. And I really hope that many of you will, at least some of you will join. It's frustrating. I have no idea of how to keep track of your what you're going through and how you're doing. I'm really worried about some of you. I mean, not personally, because I don't know any of you, but the situation is dire to many people, and many people are stressed and so forth. So I'm really hoping all of you are okay. Okay, I'll stop now and I'll see if I can somehow make this make this